Okay, so this video is going to show how to analyze a video with the rotational motion. Alright, so first thing what I'm going to do is crop the video that I've got. So I'm going to go to like online video cropper or something like that. This is just a quick way to reduce the size of the video so that the program doesn't struggle so much. So I'll take the file which I've put on my desktop here and drop it in. And here's my slow motion video, and I'm just going to choose a section of it that's not too long. So maybe about, that's a second. Let's do maybe 5 seconds. Maybe 8 seconds worth. You can check that we've got nice rotational motion there. It's not accelerating, speeding up or slowing down. I might do 10 seconds. Like that. I'll keep it in the original scale. Can I reduce? I can reduce it actually, make it smaller. I only really need the middle of it. Like that. I'll keep the voltage and the current in the shot. That's probably good. And then we'll save that. And then it's downloaded it. And I'll just open that and check that it's okay. That looks okay. Cool. All right, so now I have my cut file there. So now I want to open Tracker. You should have the app installed, otherwise you can just search for Tracker Physics online. It takes a moment to open, and there it is. Now I'm going to take the file and drag it in. And this was shot on super slow motion. No, this was shot on super slow motion, so I'm just going to double check frame rate, super slow motion, Samsung S20 FE. (960 frames per second, I think. Okay, I'm gonna maximize this. And to change the frame rate, we click on this little film clip icon in the top left. And so we can change the frame rate here to 960. Okay, and then let me just remember how to do this. We add the axes. I'm just going to put them here in the middle for now, and then I'm going to double check that that's okay. This video wasn't shot perfectly squarely on, but I think it's going to be all right. Okay, and then I'll make those axes invisible. They're still there, but they're invisible. And now I want to track this black dot. I want to choose a point on the black dot that I can easily find the same point each time. So I'm going to choose the end of the kind of trail of the black dot here. That's probably small enough. All right, and then click Track, New, Point Mass. And then hold down Shift. And the cursor should become a crosshair when you hold down Shift. And I'll go from the back of this trail here. Is that the best point? Yeah, maybe. I'm going to try to locate the same point in every frame. How many frames have I got here? Okay, I'll go for a little while, just to make sure that the angular speed is constant-ish. Okay, so now that angular velocity is considered positive when it spins anti-clockwise, so this is going to be a negative angular velocity, but that's okay. Okay, I think that's probably enough. Now, the x and y, they look like nice sine and cosine curves. I'm just promising. I'm going to change to one plot here. And I'm going to maximize that by removing the data. Oh, by the way, if you want the data, you can choose it from a table here. From the columns. So we want omega. So omega is in degrees per second. I want to change that to radians in a moment. Maybe angular acceleration to make sure that's close to 0. Okay. And maybe theta as well. So this data can be copied into Loggerpro, so you can plot the graph straight into Loggerpro. But we don't need to do that for now. I'm going to remove that, well, not remove it, but minimize that data so that I can see my graph. And I want the, first I want to change the settings. I need to remember how to do this. Is it here in properties? No. File, edit. Somewhere we can change it to be radians rather than degrees, and that'll be much better for all of our clip settings, I believe. Nope, not clip settings. Sorry about this. Coordinate system units. Yes, here, radians. So under coordinate system units, you can change it to radians. And then we can go here to angular velocity in radians per second now. But that's a bit of a mess, as you can see. But if we go to rotation angle, we can see that the angular velocity is actually kind of constant. The only reason the angular velocity looked so not constant is that it automatically zooms in. So if we reduce the scale here, so we include the origin, you can see that it's kind of sticks between 4 and 3.5 for most of it. But if you want a better estimate, you can go to rotation angle. And this is angular displacement against time. So if we fit a line to this, that will give us an estimate of the angular velocity for this trial. So to do that, we click View. Well, to do that, firstly, you could go and you could just remove any columns that are not relevant. We want angular displacement against time, so we just take away everything that's not relevant. So now we've got time and angular displacement. If you want to get an accurate estimate here, you just press Control or Command A and then Command C for copy, and we can stick it into Loggerpro if we want. I'll show you another way of doing it afterwards. So here's the data. We'll make that fit the whole thing, and then we'll fit a straight line to it. And here you can see the slope is negative 383. And we can maybe rename these things. This is the time in seconds. And it was spinning really quickly, so it's very little time that's passed. And this is the angular displacement in radians. So you can see that the angular velocity is negative 383.1 radians per second, and the bit of the video that I've tracked was between 4 and 5 hundredths of a second with all those points. So this is you can see this is a pretty good fit, and that gives us a pretty good estimate of the angular velocity. So that's one way of doing it. You can do it in Loggerpro. Another way you can do it is if you go just in the software, you can go very quickly, View, and choose Data Tool Analyze. And you can now see the graph in here. Choose Analyze and go Curve Fitter, and we'll fit a line to it. And you can see here we've got 3.831 times 10 to the power of 2, so 383.1. Is that the same as we got here? 383.1. So we get exactly the same, which is promising. And so yeah, that's how we can quickly work out the angular velocity. We can also show that the angular, what is it called? The angular acceleration here is close to 0. Which we do like this. So you can see that that's kind of centered around 0, right? It looks like it's accelerating a little bit, but that's because of my slightly inaccurate placement of the track for each point. So you don't need to track that many points. I cropped like 10 seconds worth of video, but that's a lot of frames, and I could have gotten it with fewer frames. So I could have done this more quickly and efficiently if I'd done fewer frames. I hope that clarifies everything. Let's just think, is there anything else I would need to explain? The size of the video frame doesn't actually matter for the angular velocity, because it's going to be rotating at the same rate no matter how big it is. So you don't really need that. So I think that's actually all you need. Cool. Good luck with your analysis.